This is a theoretical work about optimal statistical hypothesis testing for social choice. So social choice is a very general problem beyond presidential elections that happens very often in real life. For example, suppose your school has effective candidates opening, and there are 3 candidates come for the interview, maybe remotely, say A and B and C. After they have done the interview, the committee members is going to vote to decide the winner. And every committee member is going to use a ranking over the candidates to represent his or her preferences. For example, the first guy says, I prefer A to B to C. And then we're going to apply a voting rule on the reported preferences to select the winner. In this case, if you know social choice, this is the border rule, and the winner is going to be A. And in literature, people have thought about all kinds of criteria, for example, statistical quality of the winner, and fairness, and also computational complexity. And as the title suggests, this work will mostly focus on the statistical optimality of social choice procedures. And the problem can be dated back to 250 years ago to the Condorcet theorem, which was said to be proved formally by Laplace in the 19th century. So the jury theorem basically says that there are 2 candidates, and one of them is the correct winner, and there is probability p strictly between 0.5 and 1, and then everyone independently vote for the correct candidate with probability p. And the jury theorem just says that when the number of candidates n goes to infinity, the majority rule reveals the ground truth with high probability. And in modern statistical terms, it really just says that the majority rule is statistically consistent with respect to this very simple model. And since then, there's been a large body of literature in statistical approaches to social choice, and especially in the 20th century. So most of the previous work focused on the maximum likelihood approach. And one of the things that is not so great about MLE, which by the way is always mostly great, but sometimes it's not optimal with respect to evaluation of frequentist measures of optimality. And we know that these are 2 most dominating schools of thought in statistics. And there's been some work in Bayesian approach to social choice. And as we know that Bayesian approach is sensitive to the choice of the prior. And the frequentist approach has been much less explored and is very robust. And as Lirong commented in 2005, that a frequentist is just a Bayesian trying to do well against any possible prior distribution. So I'm not advocating one or another, just saying that the MLE approach and the Bayesian approaches have been discussed and studied in literature, but not so much from the frequentist point of view. That's the motivation behind this paper. So, our contributions, we've set up an optimal statistical hypothesis and test framework for social choice, and we have characterized an optimal tests under 2 commonly studied models. One is called the Mallows model, the other one is called Condorcet model. As we've seen very soon that optimality is measured by UNP, uniformly most powerful test. So this is Mallows model. It has a fixed dispersion parameter phi strictly between 0 and 1. And parameter space composed of all linear random orders of rankings over the candidates, and a sample space also composed of ID generated linear orders over the candidates. With respect to the following probability that given the ground truth is W, is ranking, the probability of generating a ranking V is proportional to phi raised to the Cantor distance between V and W. So the Cantor distance is really just the distance that measures the number of pairwise disagreements between V and W. It's just very natural measure. So very quickly in the introduction to the hypothesis testing framework. So I'm not going to repeat the standard framework and size and power, but just quickly remind you guys what is the uniform most powerful test. It's a pretty nice test, FUMP. Now we consider the randomized test functions that Pareto dominates all of the table tests with size that is less or equal to alpha with respect to power. So in other words, it has highest power for every theta in each one for all with respect to all tests whose size is less than 1 alpha. So it's a very strong notion of optimality, but usually a UMP test does not exist. We'll be very lucky if it exists. Okay, so here's the setup for social choice. And I'm going to have 2 settings. One is called the winner test, and the one is called the non-winner test. For the interest of time, I'm going to focus on the non-winner test, which is trying to prove that a given candidate A is not the winner. So how do we do that? we're going to set H0 to be the case that A is the winner, so that we want to reject it. And the H1 just means that A is not the winner. So in other words, in Mallows model, this can be done very naturally, where H0 is set to be all rankings are, well, the candidate A is ranked at the top. And the main results are characterizations of UMP whenever they exist, for winner test and a non-winner test, with respect to Mallows model and Condorcet model, respectively. So here you can see this is the characterization table. Well, sometimes we have the yes and the no. Yes and no says that UMP tests exist for some natural setting, but not every setting. And yet, this here yes means that UMP tests exist for the complete natural setting, which the details in the paper, but I'm going to very quickly describe the Mallows non-winner test in the next slide. Okay, so here's the main theorem, which might be a little bit complicated, but it basically says that under Mallows model and the non-winner test the UMP exists if and only if there exists a set of candidates B, such as for every ranking R in the alternatives hypothesis, the candidates ranked above A should be exactly B. So to give you an example, UMP test exists when H0 is A is ranked at the top. Remember, this is a non-winner test. And H1 is A is ranked at the bottom. And then you can see that this set B is that all candidates except A. And as another example, UMP does not exist when H0 corresponds to, again, A at the range top, but H1 corresponds to the complement of H0, because sometimes A is the candidate is ranked above A in some rankings H1 are not exactly the same. Okay, so whenever UMP exists, we actually can characterize it as you can expect. It's some sort of likelihood ratio test, but here we can interpret it in terms of social choice. It's going to be a threshold function, right? So whenever this preference profile P satisfies some condition, we can count the total number of candidates in B that is preferred to A. And if this number is larger than the threshold, you can output 1, which is retain, which is reject. Otherwise, if it's strictly smaller than K, you're going to retain. And if it's exactly K, you're going to have some probability that is calculated very carefully to accept it. Okay, so very quick summary. We have proposed the hypothesis testing framework, and for future work is computation testing for multiple hypotheses for social choice and other models. Thank you.